Today I want to run through with you one method of solving the linear programming problems that we developed that will give us the solution to a finite game. We start with a matrix A for a finite game, an m by n matrix. We assume the value of the game is positive. As we talked about when we developed this, all of this will work only when that value is positive. If the value is not known to be positive, you can just add a constant to every term in the matrix to increase the value to the point where it's clear that it's going to be positive. And then just remember, if you do this, once you've solved this new game that you create, the optimal strategies will be the same as for the original game, but you have to reduce the calculated value by the amount that you added to each term. Our objective function will be just the sum of m variables x1 plus x2 up to xn. And we want to minimize this objective function subject to these constraints. We have n linear inequalities as constraints, and we have our normalization that all the variables are greater than or equal to 0. Once we find the minimum of our objective function, you can recover the value of the game as just 1 over this sum of the x's, this minimum value for x1 plus x2 up to xm, and you can recover the optimal strategies. This is for player 1, for player 1's mixed strategy given by the vector p, where each pi is the value v times x sub I. p1 is vx1, p2 is vx2, etc. Remember, at the same time, we want to solve the dual problem, which is to maximize this objective function, y1 through yn, the sum of y1 through yn, subject to these m linear constraints, and the normalization condition, of course. And when we find the maximum for this objective function, you can recover the value in this way, and that, of course, will be the same as the value we computed before, but now you can compute the optimal strategy, or an optimal strategy, I should say, for player 2 by taking each of the y's and multiplying it by the value v to get the probability q sub j, the probability that player 2 should play column j in this optimal strategy. Now, the simplex method, or we'll show a version of the simplex method, is to set up what's called the tableau, which just has our matrix here. In the middle, on the left, you see the variables x1 through xm. On the right, you see the variables y1 through yn. We have 1s on the outer edge on the right and minus 1s on the bottom edge. And it's very important there's a 0 here in the lower right. Now, this 0 will keep track of our, what I'll call kind of a current value of the objective function. The idea is that as we proceed through the steps in the simplex algorithm, this number in the lower right will change. It will, in fact, in the way we've set things up, always increase until we get to the maximum for, in this case, the y1 plus y2 up to yn. Each time it will represent the sum of the things in the edge here on the right, or the edge on the bottom, only for those variables which have switched in locations from the x's from the left up to the top, or y's from the top down to the left. You'll see as we run through the algorithm how that works. Now, I'll run through the steps of the algorithm. They're all written down in the book as well. And let me say, before we run through all these steps, it's not going to be necessary as far as exams in our course, Math 437, is concerned, that you memorize these steps and be able to execute the dual simplex algorithm on your own by hand without any help. You won't be asked questions that require you to do that. But it is a good thing to take a look and see how this can be done. And as I've mentioned before in class, in our Zoom meetings, this can be done, or has been implemented, in many, many different ways with computer programs of all sorts. And if you're ever actually using the simplex algorithm in the real world, you'll want to probably use one of those. So here's the way one can actually compute all of this by hand. We select an entry in the interior of the tableau that we call a pivot. Maybe this one here. but it has to satisfy the following conditions. The border number in the pivot column must be negative. You must have a negative number below it, there in that bottom row. The pivot itself must be positive. The pivot row must be chosen to give the smallest ratio of the border number in the pivot row to the pivot. If you take the number of the pivot row, divide by the pivot, that must be the smallest among all the possibilities in this pivot column. Then we're going to do the operation, the pivoting, as follows. We're going to replace each entry not in the row or column of the pivot by this formula. Now that's shown down here in this diagram. If you take the pivot and you take some other entry Q, find these two other numbers, consider these four numbers, the pivot, the new entry Q, not in the same row or column, the thing in the same row is the pivot, but the same column is your new choice of number. The thing in the same column is the pivot, and in the same row is your new number. And you replace that new number Q by Q minus RC over P. You take this Q, subtract the product RC divided by P. In the pivot row, you replace every entry other than the pivot by that entry divided by the pivot. So you're going to place R by R over P. In the pivot column, you're going to place each other entry in the column, like this number C, by minus 1 times that entry in the column divided by the pivot P. And remember, of course, P has to be a positive number, so all of this will make sense. Finally, of course, we have to replace the pivot value by its reciprocal. P becomes 1 over P there. So these four numbers transform like that. It's not just four numbers, because there will be lots of other things in the pivot row, lots of other things in the pivot column, and many different choices for Q. Q could be any entry here that's not in the pivot row or pivot column. So you have to do this procedure for each number, not in the pivot row and pivot column. So in fact, you'll be modifying every other entry in the tableau, all of the numbers in the tableau, and this includes the entry in the lower right. Here's another key step. You exchange the label on the left of the pivot row with the label on the top of the pivot column. Let me show you back here how that works. If this number A22 is your pivot, you take that X2 and you move it up here. And you take Y2 and you move it here. So we change those entries as well as modifying each entry in the tableau. We keep doing this over and over again. How many times? Well, as long as there are any negative numbers remaining in the lower border row, that tells us we go back, we pick another pivot, we do the exact same rules, and then we just keep doing that as long as there are negative numbers in the lower border row. Once we have only positive numbers in that lower border row, we stop. Then we can read off the solution. The value V is the reciprocal of the number in the lower right corner. You can find optimal strategies for player 1. How do you do that? For player 1, you look at those variables for player 1 that end up on the left side. They receive probability 0. Let me show you here. On the left side, we started with all the x's. At the end, if there are any x's that stay on this left side, that corresponding p for player 1 will be assigned 0. And in exactly the same way, we started with all the y's on top. When we've finished the procedure, any y's that stay on top will correspond to probabilities Q for the different columns for player 2 that we'll assign a 0 to. For the ones that have changed, for player 1, those that end up on the top, they receive a value which you can find by taking the bottom edge in that row and dividing by the lower right corner. So let me again go back here. When you have switched an x from the left side to the top, that will now get a non-zero probability, and it will be the number that's down here. Remember, that will end up positive when you've stopped, and then this will have changed to something else. Remember, this is just 1 over the value of the game at the end. So when you've finished the procedure, we'll assign the probability P2 to be this entry in the bottom row divided by this, in other words, the value V times this entry. And we do that for each of the x's that has moved to the top. We find the corresponding probability. And similarly, we do the same thing to find player 2's probabilities in an optimal strategy by taking all of the y's that have moved to the left, looking at the corresponding number on the right, and dividing by the entry in the lower right, or in other words, multiplying by the value of the game, V. That's really all there is to it. Now, that seems a very mysterious algorithm, and we can talk a little bit later about where that comes from. But let's see an example as to how that might play itself out. Here's a numerical example. Now, this numerical example is based on the game with matrix 2, 1, 2, 1, 3, 0. This is a two-player zero-sum game where we have these 2 choices for player 1, 3 choices for player 2. Now, I wanted to look at this example with our dual simplex algorithm because this is a game which is non-trivial, but we can certainly solve it entirely by hand relatively easily. Take a second and ask, what would you do to solve this game? You probably notice pretty quickly that column 3 dominates column 1. So you would probably eliminate column 1 and you would reduce it to and you'd remember this is row 1, this is row 2, this is column 2 and column 3. We've eliminated column 1. And now this is a 2x2 game. It has no saddle points, so we know that an equalizing strategy is the optimal strategy. We have straightforward formulas to find the value and the optimal strategies in this case. The optimal strategy here, the value of the game, I should say, is the determinant, which is 0 minus 6, over this minus this, plus this minus this, which is minus 4, which is 3 halves. The value of this game is 3 halves. What are the optimal strategies? Well, once you kind of know the value, it's very easy to find the optimal strategies, which have to be equalizing strategies. The optimal vector P should be what? Well, for row 1, to have 3 halves be the equalizing strategy, you would want 1/4 times this plus 1/4 times that. That would be 3/4 plus 3/4. And you would want 3/4 times this plus 1/4 times that, which would again give you 3 halves. So for this probability vector 1/4, 3/4, it's very easy to see in your head that you get a return of 3 halves regardless of which column player 2 picks. Similarly, if Q is the vector 1/2, 1/2, then whichever row is played by player 1, the return is either 1/2 of 1 plus 1/2 of 2, which is 3 halves, or 1/2 of 3 plus 1/2 of 0, which is 3 halves. So we found the value of the game and we found optimal strategies. That was all pretty straightforward and easy. Let's see what happens when we use our simplex method. Well, we started with the tableau as set up by putting the game matrix here, the variables x1 and x2 there, y1 through y3 on top, and then we just choose a pivot. I'm going to choose for my first pivot this number 2. Why? Well, we can pick any column where there's a negative number down below. Let's say we pick the first column, and we want to look at these ratios, 1 over 1 and 1 over 2. We want to pick the smallest, that's clearly 1 over 2, so we can choose 2 as a pivot. Remember, when we modify things, one thing we do is we take the pivot and use its reciprocal. That's good. Then we change anything in the pivot row by just taking the number in the pivot row divided by the pivot. That's the 1 divided by 2 gives us another 1/2. The 2 divided by 2 gives us a 1. The 1 divided by 2 gives us a 1/2. I've already printed in a few of the entries. In the pivot column, we replace the entries other than the pivot by minus 1 times that entry divided by the pivot. So the 1 becomes minus 1/2. This negative 1 becomes minus 1 times minus 1 over 2, which is 1/2. And then we look at the entries that are not in the pivot row or pivot column. For example, this 3. We look at these 4 entries, the 2, 1, 1, and 3. This 3 is our what was called Q in the description of the pivoting process. We replace the 3 by 3 minus this times this, the 1 times 1 divided by 2. So that's 3 minus 1/2, or 5/2. What about this 0 here? Well, now we look at these 4 entries, the 2, the 1, the 2, and the 0. Those are the ones in the pivot row and the new entries column, in the pivot column and the new entries row, and of course the new entry there. This 0 gets replaced by 0 minus 1 times 2 over 2. That's 0 minus 1. So it just becomes a minus 1. And finally, don't forget to modify the entry in the lower right. For this 0, we look at these 4 entries, and we replace that 0 with 0 minus this times this over this. That's 0 minus negative 1 times 1 over 2. So it's 0 plus 1/2. That goes up to 1/2. And now we've got our entire second tableau. Oh, we're missing one entry. We have to replace that minus 1. I'll look at that in green here. For the green ones, to find the new value for that minus 1, we look at these 4 entries, and we will replace the minus 1 by minus 1 minus negative 1 times 2 over 2. That's the same as minus 1 plus 1, which gives us a 0. So now we really have replaced the entire tableau. The question is, what do we do next? Well, we see there's still a negative number in this lower row. We keep choosing pivots and doing this operation until all the numbers down here, until there are no negative numbers down here. If they're all positive, we stop. If there's a 0, we can stop, or we can look for other solutions. We're not going to deal with that now. Here we have a negative number. Well, let's look at this column. We have a 5/2 and a 1/2. If we choose the number in this column with the negative value down below, we ask which one of these has the smallest ratio of the entry on the right with that number. Here the ratio is 1/2 over 5/2, that's 1/5. Here the ratio is 1. So we have the smallest value here for this 5/2, which will be our new pivot. And so what do? Remember, we replace the pivot by its reciprocal. We replace everything in the pivot row, this negative 1/2, negative 1, and 1/2, we replace with the quotient of that number over the pivot. Here we have the negative 1/5, negative 2/5, and 1/5. We replace everything in the pivot column by minus 1 times the entry over the pivot. So minus 1 times 1/2 over 5/2 is minus 1/5. Minus 1 times negative 1/2 over 5/2 is positive 1/5. And we keep doing that then for every entry not in the pivot row or pivot column. We use that other procedure. Let me just show you, for example, the important case of what happens down here in the lower right. How do we compute what to replace in the lower right? Well, we look at that 1/2, our pivot, and these 2 entries from the corresponding rows and columns. So we replace 1/2 by that entry 1/2 minus the product of negative 1/2 times times positive 1/2. Let me be sure I write this correctly. Divided by 5/2. That's the same as 1/2 plus 1/2 times 1/2 divided by 5/2 is like multiplying by 2/5. These cancel. We have 1/2 plus 1/10. 1/2 plus 1/10 is 5/10 plus 1/10, which is 6/10 or 3/5. And that's how we get the 3/5 down here. And again, we do that for every entry outside of the pivot row and pivot column. Don't forget, I think I forgot to mention this before. In our first step, let me go back. When we chose our pivot 2, we had to replace the x1 and y1, which we did here, to get these new ones. Now don't forget, in this step, we have to switch the variables x2 and y2. So we moved y2 down here and x2 up there. So we've got this third tableau, and there's still a negative number at the bottom. So we move again. Here I've just rewritten the same third tableau. That's the same as the one at the end there. And we choose a new pivot. Well, what should we choose as our new pivot? We look at the column here with the negative number at the bottom, and we have only one positive number up here. This will be our new pivot. Again, we take the reciprocal of the pivot, and we go through all of the other steps just the same, and we end up with this tableau. And I'll say this is our final tableau because we have all positive numbers here. Well, what does that mean? Since they're all positive numbers there, we stop and we say the value of the game V is the reciprocal of this entry in the lower right. We have x1 and x2 up top, which means P1 will be 1/2 divided by 2/3. And 1/2 divided by 2/3 is just 3/4. P2 is this entry below x2 at the bottom there, 1/6 divided by 2/3, which is just 1/4. And for player 2, notice we have just the variables y2 and y3 here. y1 is up here, so y1 will be 0. In other words, q1 will be 0. q2 will be the entry across from y2, 1/3 divided by 2/3, which is 1/2. And q3, similarly, is the entry over here to the right of y3, which is 1/3 divided by 2/3. Again, it's 1/2. These are optimal strategies. And that's exactly what we found before. Just to remind you, from this game, we reduced it to this, and we get exactly the same value and exactly the same optimal strategies by analyzing that 2x2 game. Now, I want to say a few quick things about this simplex method. These steps were pretty mysterious, the way they're just described in the book and the way I showed you how to implement them right here. But they really are implementing an algorithm in which we're looking at this simplex. In the last video lecture, I kind of described what we mean by the simplex. If you write all of the, what we call the feasible set, the things that are included in all of these linear inequalities, they form a region. If you have only 2 variables, a region in the plane. In 3 variables, it's a region in 3-dimensional space. If you have 4 variables, it's a region in 4-dimensional space. If you have 100 variables, it's a region in 100-dimensional space that you get by intersecting a whole bunch of half planes or half spaces or half higher dimensional spaces. And this thing you get by intersecting these half spaces is called a simplex. And to maximize or minimize our objective function, we know that that maximum or minimum has to occur at one of the vertices, by which I mean an intersection here, or a corner point in this simplex. So you can kind of think of what we're doing as moving, starting from the origin here, moving to different corner points, trying to find how we can find the corner point which maximizes our objective function. One thing you might think is we could just try them all. The problem is there are going to be an enormous number of them, a number that grows exponentially as the size of the matrix grows, exponentially in terms of the data or the number of rows or columns. And so that can become very impractical for large matrices. The simplex algorithm usually completes itself very quickly, certainly in polynomial time. The problem is, in the worst case scenarios, it's still exponential. It doesn't give you an actual polynomial time algorithm that's guaranteed to solve any linear programming problem quickly, but it solves almost all of them very quickly. People have studied this algorithm quite a bit, and it's a very strange thing in which it almost always runs very quickly and efficiently, though there are worst case scenarios that one can construct where the number of different, in this case, pivot operations grows exponentially, and it becomes very, very slow to operate, ridiculously so. But that's only in these worst case scenarios. In any practical situation, it tends to run very quickly. You saw we only had to do three pivoting operations.